Howdy, everyone. So we're glad to have Dr. Fan Li give a talk today. Dr. Li got her PhD from Johns Hopkins University, and then she did a postdoc with John Rubin at Harvard.
No, not John Rubin. Alan Laslavsky.
Okay, all right. You have worked with
Yeah.
Okay. Yeah, and so she joined Duke University at the year of 2008, and she's now a full professor at Duke. She's a leader in the research on causal inference, and she is now also an ASA fellow and AE for JASA, and she has many collaborations with pharmaceutical companies and
mostly health data. just started with them.
Yeah, so she's going to talk about the addressing selection bias in the cluster randomized trials. Yeah.
Thanks, Guyen. Thanks, Guyen, for the invitation, and just so nice to come here, see many familiar faces, because I think Texas A&M is your department is one of the Bayesian base camps. Like I can see many Bayesians, and over the years I pretend to be a Bayesian. I'm a philosophical Bayesian, but actually my heart is in causal inference. So anyway, it's just very nice to come here and talk to you. And so today I'm going to talk about something. The style of today's talk is, again, you see the topic. It's a class randomized trial. Again, I'm not I try to hide most of the technical things and try to give a story. So I will try to be slow, and and this is something I'm recently just actually now doing. And feel free to stop me. And this talk will be the hallmark of many of the causal inference studies. Like technically it might not be sophisticated, but the thoughts, the difficulty or the challenges actually in framing the problem and make things clear. So we'll see how it goes. And so this is a joint work with my former postdoc, Georgia Papadomiroglou, now at the University of Florida, and my former student whose name is also Fan Li at Duke Yale Biostat. And so let's get started. So just some quick background. Again, I know most of you probably are not familiar with causal inference, so I can try to give this a big picture of what kind of problem we're dealing with. So randomized experiment, of course, are the gold standard for evaluating causal effects for treatment, dated back from Fisher, and then you have Neyman, all these giants. And then why randomization is so important? It's because it guarantees the treatment arms, they are comparable in both measured and unmeasured covariates. Okay, so this is, of course, then the standard analysis, because it's you're comparing oranges and apples and apples. So the thing is, once you do the experiment, then you can have treatment group and control group. You just calculate the difference in mean in their outcome. Then you're done. That's your causal effect. You don't have unmeasured confounding. So of course, sometimes you have chance imbalance. Like change in the covariates, but that can be easily adjusted use on the ordinary square, or you can do re-randomization. Again, we have an expert, Trenzhou in the department, who actually did some very nice work in that. Right, but that's all easy. So, but there are often challenges. There are many challenges of randomized experiment, but today I'm focused on this type of class randomized trial. So often the individuals, they're clustered. Like they're in classrooms or in hospitals or in villages. Like in social science, they often do the econ villages. So it is pretty difficult to randomize individuals. Like if you go to a village, you give some villagers a pill, other villagers in the same village not pill, then that doesn't go well. So it's just infeasible to do that. And second, when the units they're clustered, often there's contamination with the class. Again, like the neighbors might share the pills and stuff, right? So this is all kind of issue. And then that's why cluster randomized trial become increasingly useful. We call CRT. So the all units, so you randomize instead of units, the individuals, you randomize clusters. Okay, so the CRT, so all the units in a class receive the same treatment. So the CRT is easier to implement, and it also avoids contamination within a cluster. So this has become very popular now in health studies. Because in health studies, often the patients are clustered in hospitals, in clinics, or in health systems. So this is a natural kind of clustering there. But well, my experience with health studies, they often don't even, they at most run a random effects model. So that's how they deal with the clustering. But in the randomized experiment, this become a bigger issue is in health studies. So the individuals are often recruited after randomization. So this how you conduct the study is you first get a bunch of hospitals say you agree on participate in this. And then you only after that they go to recruit patients into the study. So you actually do the randomization right before you recruit patients. That's the first thing. And second, a lot of the treatment they are not blinded. I'll give you an example in a moment. Because of this become the so-called post-randomization selection bias. Essentially, individuals, they will self-select whether to participate in this randomized trial, because you need to agree to provide your data into the study, right? And also they might actually see, or depends on what they can see what kind of treatment intervention this cluster gets, so they might choose. And so because of that, randomization, the key point of randomization is treatment group and control groups, they're similar. There's no selection bias, but this kind of breaks that. And this bias happens after randomization. So recruited treatment and control arms might be systematically different. I just give you this one example. Actually, Shami done some work while she was at Duke with me. So this study motivated me. Motivating study is Duke conducted a big class randomized trial. So the background is P2Y12 inhibitor is a common drug for patients with heart disease, MI. So the drug is not very, it's not very comfortable thing, like you have heartburn and stuff, right? So and also it's expensive, so you need to pay some reimbursement, or you still need to pay some copay. So many patients actually don't keep taking it, like they take it on and off. So that's really not a problem. That's really a problem for doctors because they think this drug is useful. But the so-called medication persistence, essentially how persistent they're taking the drug, is a problem. So they did this Artemis trial, actually funded by a pharmaceutical company, and they spent $80 million on this trial, and it turned out to be not a trial. But let's see. So the goal of this trial is they try to. So the idea is that if I give if I give the patients reimbursement, so that they don't need to pay copay, maybe that can help them actually to better take the drug. So that's the whole idea, right? So the goal is try to improve, provide the intervention here is to give the reimbursement of the copayment of the drug. And the goal is try to improve the medication persistence of this drug. And of course, the main goal is really try to reduce the major adverse cardio events, it's like heart attack, that kind of thing. Okay. So they recruited 300 hospitals, and then they randomized at hospital level. Okay. So the intervention is for the participating patients in the intervention hospital, they get vouchers to fully reimburse their copayment for this drug. And if you're a patient in the control hospital, you get help, the Eurocare. So they totally recruited patients to 10,000. So on average, it's like each hospital has 30 patients. You can see that in any hospital, we probably have more than 30 heart disease patients. So it's actually most of the patients decide not to participate in this study. And obviously, this intervention is not blinded, because the intervention is you get money, right? So then people know actually exactly what intervention they get. So the challenges turn out to be, it's much more difficult, challenging to recruit patients into the control arm. The control arm, you get nothing, and you still need to consent to provide your information. Who would do that, right? So it turns, and then like in the middle of the study, they already find halfway through the study, they already find that they can recruit like more than double the patients in the intervention arm than the control arm. And then they have to increase the number of the intervention hospital in order to, because they want to keep the treatment arm and control arm, the sample size the same. They have to do that. So the point is that there's two groups, treatment arm and control arm, even though this is a clustered randomized experiment, they start to show difference in the background characteristic. So they find out there are some imbalance in some, they think are quite important to the investigate important baseline characteristics, like the MI history and the race. So I have a quick, like this is a big table. That you can see that again it's small, but the key point is that there are a few like their race or their college level, their comorbidity, their previous disease, and all of that. There are some differences because if you have a randomized trial when with this large size, you would expect that all of those are pretty well balanced, the treatment group and control group balance. But you can see that there are clearly some differences in those baseline characteristics. So that becomes a problem. That's where actually the investigators, the doctors come to me. They were worried that they actually wrote a JAMA paper on this, just calculate the difference and difference in mean. That's it. But they're worried that whether this standard ITT, the difference in means actually adequate, whether there's selection bias, like whether they're doing something correct. They did also the standard ordinary square adjustment. So then that become a problem. So they asked me that whether this standard ITT analysis is adequate. And then I read the literature, realized this problem is actually pretty common. Before I move to this notation, this is pretty common. Actually, in class randomized trial, because of the way you first assign, randomize, and then you recruit patients, this kind of problem of post-randomization selection bias is common. But the literature doesn't, at least as far as I find, like they don't have a systematic way of addressing it. They don't even know what actually are their estimates. What the IT, they say, is the ITT analysis enough? The question I think they should ask is, ITT, like this difference in mean is estimated, but estimated of what? You first need to ask, like you say, if this is biased, but what is your target? What is your estimate? In causal inference, we always talk about estimate first. So like I find there's no such definition or very clear definition. So that's how I come into this problem. So some notations always. So we have this units in the clusters, and I didn't use the IJ, that's double index, because for notational reason. Anyway, the QI is just class membership of units, so it can be 1 to J, right? And then among the J cluster, among them M randomized into the treatment, and this weird notation of J, I, C. C is to kind of emphasize that it's a cluster level. So you have then the J minus M randomized in the control. So ZI is a binary assignment for each treatment. So like if you're in the J's, if you're in one cluster, then your assignment is the same as everyone else in that cluster. Okay. So this is all the notation. The key thing is you have this individual assignment notation, and X, of course, is our old friends. The old friend observed covariates, so it can be in individual level and cluster level. So Y is just outcome. So the key point here is this is all kind of known. The key point in here, there's R. So this is an indicator. The post randomization recruitment status. Basically, you can be in this cluster, but then whether you agree, like R equals 1 is recruited. You decide you decide to enroll in the study, and R equals 0 is not recruited. So the key point is that, of course, we call the recruited population as or recruited sample, all the units that is R equal 1. The key thing is that usually we have information only on the people who are recruited. Because I mean, if they're recruited, they provided their data. If you say, no, I'm not gonna participate, even though you are in this population, if you are in the cluster, you still don't provide them. We don't have any information about that, okay? So this is kind of the setup. Again, any questions, stop me? Yes.
With that long list of baseline, wouldn't you expect some of them to be different anyway?
So if you have some, depends on your sample size, right? So it's actually most of the medical study, you would have chance imbalance. But this one, if you look, you would not, because this overall population, the class sample size is 300 and the total is 10,000. You would not expect this many covariates. Like you might have chance imbalance, but that often happens when you have small sample. But this is a large sample and you have actually quite a bunch. Like if you For the individual randomized experiment, what we see if you have large sample size, then normally you will not see this many covariates have like statistical significant difference. And of course, class randomized trial, another interesting thing is the effect sample size is actually clustered. It's not the overall population, but here it's kind of unusual. We have 300 clusters. So still, this is definitely like they raise the alarm because they feel uncomfortable. This is more than they can usually say. They usually might see one or two, but here and also they concentrated on things that important like the previous mental condition and stuff. So that's why it's become an issue. But I can show you that statistically, you can also show that why this can be a problem. So that's what my formulation here. So now let's set up. So let's say what people do. So again, the difference in means. So let's estimate the difference in mean of the ITT. It's just to calculate the difference between the treatment group and control group in the recruited population, because that's the only thing we have, right? So that I call ITT. That's estimated. So normally, if there's some chance imbalance in the covariates, then the standard literature they say that you can just do ANCOVA, something like this, and everything centered, and then the coefficient of the treatment will be just your standard ITT estimate. So these two things kind of, if there's a change in balance covariate, these two things will be equivalent. It's just an adjusted version. And so it's called covariate adjustment. So the question becomes, if we really worry about some post-randomization selection bias, which actually I haven't defined, but like I talk about the phenomenon, the question is this estimator still, or this estimator still unbiased for the ITT effect? But again, I need to first define what is the effect you're estimating, right? So then, yeah, what is causal estimate? So let's look at this more rigorously. So at this point, like probably most people know the potential outcome framework. Again, assuming the pseudo assumption, there is no interference, every unit will have two potential outcomes, y1 or y0. Like the counterfactuals, okay, y1 or y0, and then you only observe one of the two, that is just the potential outcome corresponding to what treatment you are getting, right? So this is the key. There are actually two causal estimates here. The first is the average treatment effect, or the intention to treat, on the overall population. Like, remember, I have this big, every hospital, they have a lot of patients. So one is the overall population. Like, so if I go back here, it will be like this 1 to n, this population. So average treatment effect is just the difference in mean, like over all of them. Okay, that's arguably this is what we want to study most of the time. But we have this bug. So the practical thing is most of the time we only have the recruited population. Recruited population is the same thing, but now conditional on you being recruited. Okay, right? So as I mentioned, that this is probably what we care because we want the larger population. But we only have the data on this guy, the recruited population. So the question becomes, are these two things the same? If they're the same, there must be some condition. Under what condition they are the same? But of course, your first thing is, if this recruited population is a simple random sample of the total population, of course, then it will be, right? But under what condition this is actually can happen? And now we can ask our question earlier asked. The earlier the standard difference in mean estimated, is it unbiased for either of this? Or maybe not. Okay, so okay, so now this is getting to the a little bit more difficult part, like complicated part, is how do we approach this problem? So I use this framework of Plain stratification, which was proposed by Frangati and Lubin in a paper 20 years ago. But and then we use this, we kind of frame this for the first time for this problem. So the key idea is recruitment also happens after the randomization. So in causal inference, if that's anything happen after the treatment or the assignment, it also have two potential outcomes. Like what I would do, whether I will be recruited if I'm being assigned to treatment, whether I will decide to participate if I'm assigned to control. So this also have two things. And then, of course, you only observe one because you only assign to one of the two conditions, right? So then we introduce this weird thing called principal stratum. What is this? This is a joint potential recruitment status under both assignments. Okay, this actually has a name. This is a pretty well-known. This is first dated back from the instrumental variable approach in 90s by Angres, Imbens, and Rubin, and the first two also got Nobel Prize last year, and Don didn't get anything for other reasons. But that's another topic. But the whole point that this idea of define something, joint potential outcome is very helpful, and I'll just show you. So if I have binary treatment here, like binary treatment is treatment group, the interventional Euro here, and also binary, like whether it's on and off, whether you get in the study or not. If everything's binary, this whole thing there are basically four possibilities. So you can kind of stratify the population into four groups. The four groups, this first one I call always recruited. Basically, those are the patients, the people who would be agreed to participate in this study, no matter whether it's assigned to the treatment group or the control group. We call always recruited. And never recruited people who, whether you're in treatment group or control group, they will not be agreed to provide data. So they're never recruited. There's this group called compliers. Compliers are the people who would not be recruited if they're in the control arm, but if they will be recruited in the treatment arm, right? Like because of the incentive of the treatment actually make them switch their behavior in terms of recruitment. And then the defiers are the weirdos who do always the opposite, right? But the key thing is, like, you can actually think of this kind of decomposition of the population. And why this is important is because if you think the definition of this guy, so because it's joint, so it doesn't matter. Like if I'm assigned to a treatment group, assigned a treatment group, this thing doesn't change, right? Because it's a joint thing. That it's like a baseline characteristic. It's just unfortunately not observed. But the key thing of this principal stratum is as the principal stratum, the membership does not change according to the actual assignment. And so it's effective a baseline characteristic. So it can be viewed as pre-treatment covariate. In causal inference, it's very important the difference pre-treatment and post-treatment. Because if anything happened post-treatment, it can be affected by the treatment. Anything happened before the treatment is, you can condition on it, right?
So I have a question. So
yeah.
the pre-treatment variable is available for everyone, whether the subject is recruited or not recruited?
I will get there. So this is a definition. This looks all fine, except that you only observe one of the two. So it's actually latent. So theoretically it's of course defined for everyone. It's just realistically, you most of the time don't see all of them. Actually, so let me get here. So I'll get there. So the point is that then we can, because this kind of pre-treatment covariate, you can define causal effect conditional on, like it's almost like conditional on a covariate, right? So you can define causal effect for each of the stratum. Like you can define the causal effect for the never recruited or for the always recruited. And they're kind of different subpopulations. That's the whole point, right? This is all nice, except that the individual principal stratum membership is not observable. Why? Because this is, unless God comes down, tells you both, right? So you actually know, so what we observe is only one of the two. Like if I'm in a control arm, then you would only observe my, like the whether I've recruited my response here in the control arm. I don't know the others. So in the end, you don't observe those things, right? So it is a latent variable. So we need, what are we going to do with that? You need assumptions, and you probably need some mixture models to do that. Okay. So again, then we need some assumptions. So the first assumption, first order, is this something called monotonicity. Monotonicity, again, does it look like this? It just say there's no defiers, there's no weirdos. Like this is very reasonable, and most of people don't like. Or in other words, like people go to a trial with good faith. They don't intentionally do things opposite. So this is a common standard assumption that we think being reasonable. Even with this assumption, in reality, what do we observe? We don't observe these potential outcomes. We observe one of the two potential outcomes for each person. What we do observe is their actual assignment status and their actual recruitment status. So if I look at the data, then you find by the definition, actually many of those cells, they are a mixture of two groups. Okay, so first, for the people who are not recruited, we don't have any data. So I'm not going to talk too much, but you can see that they are also mixture. But now let's really look at the people who they are recruited. So this information is observed. So I have the control arm, and those people are recruited. So who they be? If you are in the control arm and you actually participate in the study, you must be always recruited because there's no defiers. So if I already so nice to provide information when there's no even incentive, of course I would provide more information when I have incentive, right? So this always recruited. So this cell have only this one subpopulation. The tricky part is for the treatment arm, you have, then it's different. For the treatment arm, for the always recruited, and so for the treatment arm, yeah, those people who provide data, they might be always recruited, or they might be those compliant, because you don't know what they would do if they don't get the treatment, right? So this always, so this is a mixture. Okay, and this group, they're also mixtures. So why I do this exercise, intellectual exercise, it's because, so now you can see that this is the recruited population, the population like that. We do have data. And it only consists of two stratum, two subpopulations. They're always recruited or compliant. We cannot even disentangle them. But the key thing is, they only include two groups. But remember the overall population, like the overall population, it consists of all three stratum. So what does this say is that clearly this, when you have this kind of selection bias, when you have the selection post-randomization selection, the observed group or the recruited population is not a simple random sample of the population, the overall population. It cannot be because one consists of all three strata. This only consists two. It simply cannot be. That's the first thing. And even more important is you can see now in the control arm and treatment arm, it consists of different subpopulations. Remember, why do we do randomized trial? The whole point is that because we think that they're apples versus apples. So this means to say that you are having this, if you need people to consent to enter the study, then when you have selection, the treatment arm and control arm, they are not comparable. So that's why you cannot do this ITT and differencing means, because that would be biased. Okay, so I don't know. I always have difficulty to introduce this concept because for causal people, this is kind of pretty well known. But for people who never done causal, this is one step forward, even on top of the potential outcome, because you're talking about joint of two potential outcomes. But this is a very useful intellectual kind of framework to tell you why the bias arises. Okay, so do some. You can do some simple calculation. You can find that, okay, remember there are two different populations. One is the overall population, the other is the recruited population, and we can define the causal effect on each. So you can, so the ITT effect for the overall population is just a weighted average of the treatment effect on each subpopulation. And that's all very easy. I mean, that this is just a weighted average. There's nothing strange here. But to do this result is a little bit more tricky to get. It's basically the average treatment effect for the recruited population is the average of the weighted average of the treatment effect on the two stratum, the always recruited and compliant, because for the you don't have this never recruited population. So this is just basically a formula to show you that what kind of weighted average. So you can see that what this depends on is the randomization proportion also the proportion of the, which is identifiable, but also the proportion of the stratum, these different subgroups in the overall population. This is not identifiable. This, you don't actually have information, but this is show you that this is important, like this show you that's the relationship. So then what's the point? The point is that these two things, just mathematically, these two things, there's two different estimates. This two, if when you have post-randomization selection bias, these two groups, these two estimates are different. That's essentially, you are not at, so you cannot do, it's impossible for you to do the difference in means and claim that you are unbiased estimate something, because you're actually not. So this already say that. So the only thing this can happen is if there's overall population, there's never recruited. We know that this is not possible because there are many people who anyway would not participate in a trial. All the treatment effect is homogeneous across Australia, which is also unlikely to be the case. So the second point is that the standard ITT estimator is actually generally biased for both. So when you have selection bias, post-randomization selection bias, here basically show that what people do, this difference in mean estimated is biased. For each, like not only for one estimate, even for the estimate, like in the average treatment effect for the overall for the recruit population is still biased. So that's really say that you cannot do that. Okay, the third thing is this is systematic bias. This is different from chance imbalance. So you cannot just do an ANCOVA and hope that the bias that all of a sudden your difference in mean estimated will be devised. Okay, so those are the key insight from this exercise. I do have an example. I don't think I have time to go through, but I just have a quick. I will skip this part, but I have a hypothetical example to show that when you this online truth and this is the observed data, and if you just do difference in means, you will get bias in the case. So this is just, I'm not going through that because I have more important things to go through. So okay, now we know that the standard approach is wrong. It's biased, and then the next step is, okay, how do we correct it? Is there a solution to this? And so in order to do that, the first question is actually not to come up with the estimated. We will come up with estimated. The first question is, people do class randomized trial in hope that this is just a convenient way to implies individual to get an individual randomization, but we cannot do. So then the first order is we need to answer the question: when does class randomization implies individual randomization? This is not a given. Okay, there are conditions. So so there's some assumptions, but so again, this is so what we find, we kind of rigorize this. Essentially, this is a key assumption. The key assumption says that if there's no selection, so if the units have no selection of the clusters, like for example, if you're heart disease patient, usually patients go to a hospital not because if it's not a rare disease. Usually you go to the hospital closest to you, or like if I usually go to big hospital and stuff, right? You would not travel like 50 miles to go to a special clinic. Well, if you are not having a rare disease, but rare disease is a completely different thing. So the whole point is that we find the condition for this to happen is there should be no individual selection of cluster. Essentially, you don't choose your class, which cluster you enter. You don't choose that. If that's the case, then class randomization will imply individual randomization. But again, this is itself is not enough, right? Because this is still didn't talk about the post-randomization selection bias. But this is important for us to establish all the later results. The first thing is, if the individuals can choose whatever cluster they want according to what kind of treatment assigned to this cluster, then class randomization doesn't imply individual randomization. So this operation-wise is important for the practitioner to know this when they design a randomized experiment. I mean, this is say the same thing. Lemma basically just says and then this is not enough yet because we still need to know. Now you tell me that I cannot do the standard ITD analysis. What should I do? So we need more assumptions. Causal inference is all about characterize what it as demand and then specify the assumptions and then proceed. Okay. So what we find, this is very important. Assumptions called ignorable treatment, recruitment. Basically say that all the factors affect that whether this person being recruited in a study or not are observed. So there essentially there's no unmeasured confounding in people's recruitment behavior. So all the covariates, so this is called ignorable recruitment. Again, this ignorable, the word is from the ignorability stuff or common in combination. Basically, there's no unmeasured confounding in the recruitment process. And the other thing is called positivity. This is a technical assumption, which is important. Basically, every person has a non-zero chance, the probability of being actually recruited. This is technical, but actually also important. That's a long story. I can talk about this, not for today. Okay, so with this, the first result is kind of easy, not surprising. So remember, again, we only have data for the recruited sample. We don't have for the overall population. That's all we have. So the estimate then is actually turned out to be relatively easy. If you are somehow interested in the estimate in the recruited population, like the average effect for the recruited population, then you can actually pretty easy to do either use outcome model or IPW, inverse probability weighting. So the key thing is this thing called the working propensity score. So this is just the probability of Z equal 1, the assignment given X and the given they are recruited. So why I call it a working propensity score is this is really not a probability, because if you do a randomized experiment, then of course the probability of being assigned between is 0.5, right? So this is a working, so this is actually a summary statistics. This is just a one-dimensional summary statistics of the covariates. And this is, again, this will call working propensity. But anyway, this is a technical point. The point is that if you have this data, you calculate the working propensity score, which turned out to be actually tricky in class randomized trial. But if you get this working propensity score, then you can just do IPW or do a regression. So that is easy. That is actually not surprising because, of course, I mean, I have data on my recruited sample. You would imagine that it's relatively easy to calculate the estimate on that, depend on that sample. That's all simple, right? And you can use IPW stuff. This is all standard stuff, and you can prove things. So difficulty is really, as I said, that this recruited population is really kind of a nuisance. It's not what we started to do. We really want to know more information about the whole population, not just recruited. And especially if the recruited population is actually different from the overall population, that sounds very unsettling. It's like I do give so much money to do this trial, and then I only know information about those people who are willing to participate in the study, which might be different from the large population. What should I do? So then the question is it even possible when you don't have any information about this unrecruited population, is it possible even to say anything about the overall population? So the answer is generally it's infeasible to say because you don't have data, right? But what we find in this study is very interesting is it's actually possible to use some trick to identify the effect, treatment effect on a meaningful subpopulation of the overall population. So how we achieve that? It's almost like magic. Like you don't have data for the population. How can you do that? So the key insight is, if we go back a few slides, I hope you're still with me. But the key point is that this group, we do observe this group. They basically the control arm that are observed. So this arm, we know that they must be this always recruited. They are not mixture. Because if you already, as I said, that if you already provide data when you are not even given incentive, you of course will give the data also under the incentive. That's an alternative assumption. So the key point is this is an observed cell, and we do know these people, they are always recruited. So, but always recruited, again, the definition is on the general population, right? So that is a trick. We find that it's very useful. So what is that? What is that? So we can basically, you can reweight. You can reweight. So we know that the treatment arm and control arm in the recruited population, they're different. But we can reweight the recruited and treated arm to have the same covariate distribution as the control arm. Once we do this reweighting, also we assume that there's no unmeasured confounding, then you can actually recover the treatment effect. You can recover the potential outcome of this always recruited arm on the treatment arm. Again, this is almost like contrastive. So the whole point is that we find one group that is observed, so you can identify them, and then you can reweight their population so that they look exactly the same as the other arm. And then that'll help you to calculate the treatment group, the difference between the two. So that's a common trick in causal inference. I use the reweighting. The key thing is you want to make sure that these two arms, the covariates, are the same. So then how do you do that? The key thing is how do you do the weighting? The weighting is no longer IPW. It's a different type of IPW. Again, I write this kind of thing, this proposition. This essentially just say that when I don't have data on the unrecruited population, I can still do one thing. I can still identify a meaningful subpopulation. This basically I can identify the treatment effect on the always recruited. It's better than nothing, right? I can actually do the weighting trick. Well, we use this kind of weighting to estimate the treatment effect for the always recruited units without even data of the unrecruited population. So what should I do is you first estimate the working propensity score. I will talk about how to do that. And then the key thing is you need to define the weight. It's for the control arm, the weight would be it's the control arm, it would be 1. You don't weight anything. For the treatment arm, you actually do this kind of weight, 1 minus E divided by E. So this is always also inverse, but it's different from the standard IPW. And then you can actually prove this is unbiased. Then the weighted difference between the treatment group and control group, the recruited are the just unbiased estimated. This is all good, except how to estimate the working propensity score. So you say, oh, how about I just do a logistic regression? So this is binary. Turns out that not that simple when you have cluster randomized experiment. Because if I look at it, you can write it out, but the whole point is that when you have class assignment, you simply cannot do a logistic regression on the individual level and hope to get the working propensity score. You can prove that this is biased. So what you're going to do is you have to actually derive the likelihood of the working propensity score from the recruited sample, and then get the MOE. And this is all, again, we derived it, and the formula is long and all that kind of thing. But then you ask, like, how many, if you really want a practitioner to use this, cannot say that, hey, look at my formula of likelihood and then maximize it. It's not going to work. They want to use logistic regression. So the point is that cannot be happen. Then we find that's actually a special case when the recruitment rate, when the recruitment ratio, something like this, if it's follow exponential distribution, it's an exponential form, again, that's very simple. Then you can actually estimate the working propensity score, use the cluster logistic regression. So again, this is some technical detail, but I think it's important to talk about this. So weird enough, you still do logistic regression, but because you are doing class randomized trial, you cannot do logistic regression on the individuals. You do a logistic regression on the cluster sums. So like the covariates actually are not the individual covariate, it's the sum of the covariate in that cluster. Okay, so it's basically look like this. And that's not enough. You actually also need to adjust your intercept and stuff. So again, this is also some proofs. So the key point is that this way, if you're willing to make some assumptions, say that some technical assumptions, you can essentially tell practitioner, you can use a logistic regression to work on the cluster mean, cluster total, then you can kind of work into yes.
Oh, good.
Yeah, one clarification question. If we go to the previous slide, So is X observed,
Yeah, X is always observed. It's covariance is always observed.
always observed for R equal to 1 and R equal to
No,
0?
only for the, even for the, only for the, again, if you are R equals 0, nothing observed.
Nothing, even the baseline
No,
randomization variables are not.
Yeah, in rare case, you can go to EHR and stuff, but I mean, that's most time people don't have that. Yeah.
So then, in the next slide, when you say that X bar is the total,
Yeah, so there's like, yeah, so if this has to be the, yeah, this is
only
only,
for the recruited
Yeah.
R equal to 1.
yeah, exactly. That's actually the difficulty, the proof, like the proofs, and we find that I would be very careful with that. Yeah.
I'm just curious why you are calling this a working propensity score. Is the working part to allow for misclassification?
Oh, no, that the working, the key reason, that's a good point. The word, my reason was called the work. So because if you look at in causation, the propensity score, the definition is the probability being treated given the covariance, right? But if you think that in this case, the probability of being treated is actually randomized. So it's like 0.5. So like, but here it is purely like, but you estimate it in some sense, like it's just a one summary of it's not really a probability. It's a summary of all the covariance. It's almost like a summary statistic. That's why it's called working propensity. No, it's still actually sensitive to misspecification and all that kind of thing. But yeah.
Related to that, I'm wondering then, would you also consider a regression modeling approach and then combine them to get a double low pass system?
You're right. Actually, you can easily do that. We didn't. Yeah. So, but double robust. That's another. Double robust is the name is popular. I think they get a great name. So double robust is like you can do outcome and the weighting, right? It give you 2 chances to get things right. And I always say it also give you 2 chances to get things wrong. So and actually, I recently have a result. I find that if the overlap of the two groups are not well balanced, actually doing double robust can do harm. And that's a different story. Yeah, but technically, yes, you can easily actually combine this, particularly here. You can have an outcome model and the weighting and then combine and use double robustness. But I just don't think it's too helpful here because sadly you will see in another slide that after all this theoretical work, I find in that trial, all things work the same. But technically, yes.
So the regression modeling approach may be slightly easier to fix, right?
I still don't know. I mean, it's still you need to take into account of their clustering. But again, double robust, you still need to do you still need the propensity
I was
score,
just
right?
wondering about the other approach.
Yeah. So yeah, I think the answer here is probably we particularly notice this weighting thing, like this kind of you can do weighting, right? The different type of weighting you do that. And your point is that, well, I can just not even do weight, I do outcome regression and then maybe combine them, right? That may be easier. Yeah, we didn't do that. We know that it's possible. We didn't. It's just like it's not. This is sexier, I would say. Like because it's weighting, how do you avoid even build a model for the outcome? Because for randomized trial, I talked to the practitioner. For some reason, they're very against doing model. They feel that I'm already doing a randomized trial. Why should I still have a model? This is a very common like psych. So that like if you say you can do something weighting, they feel comfortable. Like that's I think that's also that's more technical. That's not quite technical, but that's just a practical concern. But those are all good points. Yes, you can do that. And then like I think of course you always need to prove some asymptotics to get paper published. So that's you prove that all of these things if the cluster size goes to infinity, this is all asymptotic normal and all that stuff, right? But the reality is this kind of useless. Because randomized, like this is a study, I actually have the luxury, have 300 classes. Most of the class randomized trial, they have like 20. J is 20. This definitely doesn't kick in. So there's a lot of finite sample issue. But again, we prove things for the sake of proving. And so at the end of the story is a kind of sad reality. Well, sad for me, but it's good for the practitioner, for the clinicians. So we applied this to the estimates. Remember, they come to me because they're worried that what their estimate is really biased. So so what I find out, even that I say highlight, there's some, imbalance between covariates, but they are overall it's not too bad. I mean, it's still some, but overall it's not too bad. So what we did, what we proposed, right? We find that the difference in means this is the IPW estimator for the recruited, and this is this is subpopulation for the overall population. It's not more or less the same. Okay. Again, this is actually great news for my medical collaborators, because this gives them confidence, say that, hey, whatever we are doing, even though methodology wise, is not, so I basically say that this is theoretically, this is biased. In this case, the result actually all pretty similar. Like if you do so this probably what it suggests is that like the little difference is probably indicates some homogeneity, or there's maybe the selection bias is not as bad as we thought. Okay, so that again, the interpretation of this is say reimbursement of this drug indeed increase make people or the medication adherence by 2.7%. And another funny thing is they spent $80 million on this trial. Of course, they are not like the pharmaceutical company. They're not for them. They're not doing like they want to make money, right? So they really want to see that this actually translates into reducing the heart disease. For that answer, Xiaomi knows it's no effect. It's like they find that even though they actually improve this medical adherence like by 2.5%, which is kind of important for them, it didn't make a difference. So the whole idea of pharmaceutical company to spend this much money to do this study is they were hoping that if they can do this and then prove that this reduced heart disease, then they can convince the Medicare to pay all the copay, so that then they can sell more drugs. And that they failed. Like again, even I do this kind of thing doesn't help them because I mean this I'm just looking at the secondary outcomes of medical adherence. So that's kind of the story. And I'm gonna skip this sentiment analysis. The point is that, well, the key thing is everything is rests on this ignorable recruitment assumption, which is pretty strong. And then you can do some fancy math and then do some permutation tests and stuff to see that how sensitive the results are, and the result is not too sensitive. So just quick summary. So this is kind of a story. It's just first we show that class randomization does not automatically imply individual randomization, and often it's prone to post randomization selection bias. So what we did is we clarify the different estimates and the corresponding identification and estimation strategy when you have selection bias. And surprisingly enough, this is actually the first time in the literature we established conditions that say under which the class randomization implies individual randomization. Like previously, people thought nipple around but didn't really write it out. And then we elucidate the source of selection bias using principal stratification. And I think the most important one is like has a practical meaning is when we only have data on the recruited sample, which is the case in most of the studies, we show actually how can you use weighting to estimate the treatment effect, not only on the recruited sample, but also on a meaningful subpopulation of the overall population. Like at least you can say something about the overall population just instead of saying, I don't have data. And so in practice, what we recommend is that when you suspect there are some selection bias, then you should calculate maybe all three, like the difference in means and this ITT, this IVW, and this different estimator, and then itself serve as a sensitivity analysis. If they are similar, then probably a very good sign. If they're different, then you should start to worry about whether there's sensitivity analysis or whether there's really selection bias. So again, this is funded by Picori and have some good collaborators here, and there's some references. Thank you.
Any questions?
Yes,
So to me, it seems like the modifier assumption is very important here.
so what the,
The modifier.
okay, yeah, it's,
In your context, it means that if someone is given incentive, then it is very unlikely that they will not be recruited. So like how realistic is this assumption in practice and in the real world that
Yeah.
you see this?
yeah, so that's a good question. And monomolarity assumption probably is the simplest, the assumption is the most likely to hold, like than this unmeasured confounding. So in this case, it's kind of obvious because you have financial incentive to do things. And so it's normally, this is again, we think that in the Artemis, it's definitely the case. You give money, like, yeah. So this is the easiest assumption to hold. And when this assumption doesn't hold, the problem is then every single cell here would be a mixture. And then it's much more difficult. But fortunately, in most of the, like also in clinical trial, we often have this assumption too. Essentially, where the assumption amount to assuming the patients participate in a trial with good faith. Like they don't intentionally to do things opposite. And usually the doctors feel that that's kind of the case. Like the and this is okay, but this assumption is important. If this assumption doesn't hold, then you will have to use mixture model. Like the weighting doesn't hold anymore. Like you have to do mixture model, and very often it's very hard to identify. Like the label switching is just a huge problem. But yes, this is a key assumption.
If the treatment is risky, though,
That's very good. Yes, so it's case by case. So I actually recently have another trial. It's on the it's actually breast cancer. So the two, one is like the medical, just to get medicine. The other is surgery. In that case, indeed, I actually see the opposite. But then the monotonicity is opposite. It's people more likely to avoid surgery like them. But still, that doesn't say that you are doing this like if you. But this monotonicity keeps saying that monotonicity is about you would do what you would not do the opposite of what you are trying to. So it might be like if you don't want surgery, then you might just be a never surgery person, like always surgery person. It's not like you just like who would attend a political trial just say I'm gonna do whatever you ask me to do and do the opposite. Like that the assumption is actually about that, like well that kind of people, which is but the point of like which direction of the drug you use, so like intervention and control which you take, that direction can be quite like can go either way. But that doesn't affect this monotonicity assumption, which say your hypothetical behavior of the same person on a different treatment. Yes.
Just have a quick question on this. Do you have any thoughts on how this can influence kind of the way the trial is designed and the information collected up front?
Absolutely. Absolutely. That's a great point. That's exactly what I might done. They come to me after spending $80 million, right? And then do this. The effect is like it cannot be smaller than that effect on the So what I find that this information is one thing is important. Like when they collect the data, they should ask the hypothetical question like, hey, they should collect the data. Say, if you are assigned to if I assign to the opposite group, what do you do? At least have some information of that. That's the first thing. And the second thing is like when you have this kind of problem, it's very important to bring some extra information. If they have even a little bit more extra information about this, many of the patients who are in the system but decide not to participate, if they can somehow have the EHR data, then they can actually do something nice like anchor. They can calibrate the result to that. So yeah, so in the clinical trial paper I wrote, I asked people, I say that it's important to collect the information on some of the people don't participate if you want to know anything about the whole population. And second, ask their potential compliance behavior. So yeah, so this actually even more important than this estimated, I think. If they can do the design better, they probably won't waste all this money to do the trial.
It's about time, so let's thank Ben again for a great talk. you can join her if you plan to have any further questions. Thank you.
Hello.
Yeah, I think I met you somewhere before, and I definitely know your name.
I don't remember where we met either, but yeah,
Mhm.
we will chat later also.
Yeah, sure.
Dukies.
Duke,
There's a
yeah.
lot of Dukies. He's,
Hey, yeah,
he's
so
good to see you.
Yeah, he's actually invited me to give the Bayesian conference summer school. I'm very excited.
Lots of Dukies. Smiley is here.
Mhm. Hey, well,
Good to see you.
yeah, good to see you.
Yeah,
Yeah,
great talk.
yeah, good to see you in the dinner.
It did,
Yeah,
right?
okay. So how long will you be here?
2 weeks.
Two
I'll be
weeks.
living in there in
Ah, okay.
I need to do that. Welcome.